Okay, so guys, this is a cycle L phase 1. So cycle L is the last cycle of the year. I'm going to try to finish it. Today is, what day is it? It's Thursday. Today's Thursday the 23rd. I'm going to actually try to bang it out and get everything done today. So anyway, this video might take me a long time to make. But this is a prime example of something that you will probably be able to process and understand faster than I can explain. So if you want to use, maybe some of you already do, but if you want to speed up the video, you might find that this is a good video just to speed up. So, because the concept itself is pretty simple, but it just might take me a lot of writing and explaining. Okay, so, and the notes will be attached, so it's not like you have to write if you don't want to. So estimating a definite integral. So we're going to estimate this definite integral, the integral from 6 to 22 of radical x, with a left Riemann sum using 4 subintervals of equal length. So what does a derivative mean? A derivative means the slope of the tangent line, or the instantaneous rate of change, but like visually the slope of the tangent line, that's what a derivative means. What does an integral mean? It means the area under the curve. So from 6 to 22, right, so I've given you the graph of radical x, and then they want the area under the curve from 6 to 22, all right? So guys, the area under the curve from 6 to 22 is this, it is this area. It's this exact area. So the integral itself is this exact area. But we're going to get an estimate for that exact area using something called a left Riemann sum with 4 subintervals of equal length. So what you've got to do is you've got to take this interval, and we're going to split it up into 4 subintervals. So I could split it up like this, 4 subintervals. Okay, so first subinterval, second, third, fourth subintervals of equal length. These each have length 4 units, right? From 6 to 10 is 4, from 10 to 14. Okay, so there's my 4 subintervals. Now, what does a left Riemann sum mean? I will show you. So what we're going to do is we're going to use, and if you're in physics, you may have already been introduced to this, but all right, let me just show you. So this first subinterval, I'm gonna make a rectangle using this first subinterval. So the base of my rectangle is going to be that subinterval length. Okay, so this is going to be the base of the rectangle. Now for the height of the rectangle, here's the thing, guys. You're going to have 3 options for how to get the height. You can use the left endpoint of the subinterval, you could use the midpoint of the subinterval, or you could use the right endpoint of the subinterval. And if we're doing a left Riemann sum, you're going to go to the left endpoint of the subinterval, and then that left endpoint is what's going to determine your height of the rectangle. So you're going to plug this left endpoint into radical x, and then that's going to give you this y value. So you go to the left endpoint, and then you just go up to the graph, okay? And then it's this point up there on the graph that is going to determine, so this is the height of your rectangle. And then you just complete the rectangle. So you got to go, so here's the base, you need this top to be parallel to the base. You just go horizontal over, complete the rectangle, and I fill it in. So that is my first left endpoint rectangle. All right. Now, in the next subinterval, we're going to do another one, another left endpoint rectangle, because this is a left Riemann sum. And then I'll explain more what this means in a minute, once you have seen it. So I'm going to take this base. So this is going to be, the next subinterval is going to be, that's going to be the base of my next rectangle. I've got a left endpoint and a right endpoint. So I'm going to use the left endpoint 10, and I'm going to go up to its output on the graph, and that is going to determine the height of the next rectangle. So I just go horizontal over. Okay, 2 more. So here's my third rectangle. I go to the left end point because it's a left Riemann sum. That left end point is going to be the input that I used for the height. And then over horizontal, down. Oh, and by the way, guys, the practice for this is going to be on Delta Math, and you're not actually going to do what I'm doing. It's going to be much faster what you do. And then here's the base, left end point. Okay, so here's the thing, guys. We know how to find the exact area because we know the fundamental theorem of calculus, so we could have just used that. But they're asking for an estimation. So if you take the area of each of these 4 rectangles and you add them together, that is going to give you an estimation for this total exact area under the curve from 6 to 22. So this integral from 6 to 22 radical x dx is going to be approximately, okay, now I'll say this up here. Okay, so rectangle area is base times height. So I'm going to do base times height for each rectangle. So base times height for this first rectangle. The base is the subinterval length, that's 4. And then for the height, guys, what is this length here? What is this height? This height is the y value. This height is the y value that plugging in 6 gives me. All right, so if you plug in 6, you get the y value of this point, which is also the height. So you're plugging in 6 to radical x. So you're getting radical 6. All right, so that'll be radical 6 is that height. Now, we're going to add this next area. The base is the same. That base is 4. And then the height, this time you're going to plug in 10. So it's going to be radical 10. This next area, the base is the same. It's 4. And the height, this time you're plugging in this left end point each time. So it's, you plug in 14 there, and it gives you radical 14. And then the base is the same, and then the height this time is radical 18. Now, let me save time. So you plug this all in your calculator. So this is approximately 54.3843. Now, this is an approximation. Is it an over approximation or is it an under approximation? It is an under approximation because see how the rectangles are beneath, they're beneath the graph. So there is some yellow that is like above those rectangles, which means the rectangles are, their area sum is less than the actual area. So this is an under approximation. And at the very end, guys, of this video, I'm going to show you like when you can say, like how to say to your reader, it's an under approximation because of some characteristic of the graph. Okay, so let's do, all right, a Riemann sum. A Riemann sum, it's named after the guy who, like, I think either came up with it or formalized it, because I'm sure through history a lot of people in different parts of the world came up with the same idea. But this guy Riemann, he's the one who's famous for using is a sum of rectangle areas used to approximate an integral. Okay, so Riemann rectangle, Riemann rectangle. Riemann, think rectangle. Okay, so Riemann sum is a sum of rectangle areas used to approximate an integral. Okay, guys, let's do this one. So that was a left Riemann sum. This time, estimate the same integral with a right Riemann sum using 4 subintervals of equal length. All right, so same idea. It's still 6 to 22, 4 subintervals. All right, now especially if you already have the idea, guys, maybe speed it up, if you want to save yourself some time. But this time a right Riemann sum. So for a right Riemann sum, the name left or right tells you which endpoint of the base of the subinterval you're going to use to get the height of the rectangle. So a right Riemann sum. So here's my first subinterval. Instead of going to the left endpoint and up to the graph, it's a right Riemann sum. So the right endpoint, which this time is 10, up to the graph. So this y value determines the height of the rectangle. And then you're going to go over this direction horizontal and complete the rectangle. So there's your first rectangle. The second one, it's a right Riemann sum. So you go to the right endpoint up to the graph. I just remembered something I have to do. I keep forgetting. Okay. I'm just forgetting so much these days, even what day it is. I'm sure you all are. Quarantine life. Okay, go to the right endpoint. Okay. And then right endpoint. Okay, so this time you add the area of these 4 rectangles, and that's going to give you an approximate area. Oh, and I mean this, we don't have to do this, but let me color in yellow the actual area. Okay, so the yellow is the actual area. Okay, so the integral from 6 to 22 of radical x dx is going to be approximately the sum of these 4 areas. So for this first rectangle, just like with the left Riemann sum, just like with the left Riemann sum, the base is going to be the same because we're using the same subintervals. So 4 for the base, and then height this time we use the right endpoint, so it's going to be radical 10. Plus, I'll go a little bit fast, guys, but pause the video if you don't understand something and figure it out. You could figure it out. So 4 radical 14. 4 up radical 18 I used. 18. 4 radical 22. So here, approximately 63.348, bigger than our last one. Okay, so the left Riemann sum gave us this approximation, so this is bigger. And let's think about the type of approximation. Is it an over approximation? Is it an under approximation? This time it's an over approximation. See how the areas of the rectangles are higher, they exceed the yellow area. So this is an over approximation. All right, there's 2 more types of ways of estimating, guys. Okay, so let's do them. So this time, same everything except the type of sum. So we're going to estimate the same integral with a midpoint Riemann sum using 4 subintervals of equal length. So same idea. So 6 to 22. 4 subintervals. Okay. And you could probably guess the way this is going to work, midpoint Riemann sum. So the left-right midpoint is telling you what point on the subinterval that you're going to use for the height. All right. So the midpoint Riemann sum, you're going to use the midpoint of the subinterval to go up to the graph and get the height. So this is 8. So I'm going up to the graph here. So that is going to be the height of our first rectangle. And then you just go left and right, horizontal, and complete the rectangle like that. Okay. Midpoint up to the graph. That'll be the height, that y value. And guys, notice that with the midpoint one, in this case anyway, like with this blue one especially, you could see this half of the rectangle's area is a little bit over the curve, but then this part of the rectangle's area is a little bit under the curve. So as far as over approximating, under approximating, with a midpoint Riemann sum, they would never ask you, is this an over or under approximation? Because very often you can't tell. Because one part of the rectangle will be over the graph, the other part of the rectangle will be under the graph. So you can't really tell for certain. All right, and then, yeah, so you won't be asked that. See, one part's over, one part's under. Oh, bad. Okay, so the integral from 6 to 22 radical x dx. Just like before, we've got each base is going to be 4. But then for the height, you're plugging the midpoint into the function. So this first height will be radical 8. Base, second height, radical 12. Base, second height, radical 16, which is 4. Base, and then the height is radical 20. All right? Oh, I said, they won't dock you if you say equals, I think, instead of approximation. But so this approximation is 59.0587. Can't really tell if over or under approximation. I mean, it looks to me like it's probably more of an over approximation, but you know, you won't be asked to make that determination because you can't really tell visually. Okay, so there's that. Now, last type, and then we'll move on to some other stuff. We're going to use a trapezoidal sum. Notice it doesn't say a trapezoid Riemann sum or something because Riemann means rectangle. Riemann, rectangle. They start with R. But this is going to be, of all the ways of approximating, guys, using trapezoids is going to be more exact than using rectangles. It's not going to be perfect, but it's going to be more exact. Oh, a way that you could make a Riemann sum with rectangles, a way that you could make it more exact is to use more rectangles. All right, like if we used 6 rectangles instead of 4, it would be a better approximation. If you used 100 rectangles, it would be a very good approximation. And then if you finally took a limit, if you did the limit and then you let the number of rectangles go to infinity, that is actually the definition of an integral, is doing a limit with these rectangles. So you let the number of rectangles go to infinity, do a limit that way, and then that will give you the exact area. Okay, but we're not going to do that. But yeah, that is the concept. Okay, when you have an infinite number of rectangles, that is this exact value. Okay, so anyway, trapezoids. Yeah, so trapezoids will be the best approximation with this type of finite, when you have a finite number of intervals, subintervals. So 4. So we're still using 4 subintervals. Now, this is going to look really good. All right, so for a trapezoidal one, this length of the subinterval is actually going to be the height of the trapezoid. So when you're doing a trapezoidal sum, the trapezoids are going to be on their side. So I'm going to turn my paper like this. So this is actually going to be the height of the trapezoid. And a trapezoid has 2 bases, guys. It has these 2 parallel bases. So going from the left and right endpoints up to the graph, that's going to give you the bases of your trapezoid. All right, so this is base 1, and that's base 2 of the trapezoid. And then, I think I have a ruler. I do. All right, and then let me connect, maybe as exact as I can. So I connect those endpoints of those bases. And guys, look how nicely, like this graph, radical x is curved. But with my human eye, it's really hard for me to see the difference between this curve and this line that I just drew. There is a difference. It turns out that the curve, because this is curved, it really is a little bit above that line, but you can't really see that with your eye. So we need the area of that trapezoid. And the area of a trapezoid, and guys, this AP exam is going to be open book, so you should be writing things down, that maybe you don't think you'd remember and you want to remember for the exam. Oh, and actually those flashcards at the very beginning of all this, I sent you a huge document, like a 500-page document with everything we'd done all year. And at the beginning of that document were a bunch of flashcards. So I think that would maybe be good enough. So if you take a look at those and then, write down additionally other things you'd like to have in front of you. So area of trapezoid, even if you'd like to have examples in front of you that we've done, that'd be fine. The area of trapezoid is 1/2 base 1 plus base 2 times the height. All right. So for this first, all right, so the integral from 6 to 22, oh my gosh, sorry. I have an appointment okay, I hit snooze by accident. Oh my God. One of my cats is acting up. Stop it, please, Walter. Stop. Okay, so this is going to be approximately, for this first trapezoid, it's 1/2 base 1 plus base 2. Remember, these are the bases. These are not the heights. These are the bases. So base 1 is radical 6. Base 2 is radical 10. And then the height is the subinterval length. So that is 4. Plus this next one. This is the height of the trapezoid. Remember, it's on its side. So that's the height of the trapezoid. This is going to be base 1. That's going to be base 2 of this second trapezoid. And then, I connect these. Those are pretty good straight line. All right, so let me draw the trapezoids first. Height. Okay, height. Base 1, base 2. Connect. Height, base 1, base 2, connect. Yeah, as you can see, trapezoids are a really good approximating tool. Looks almost perfect. All right, so that's the first trapezoid area. Second trapezoid area, 1/2. Base 1 is radical 10, base 2 is radical 14, and the height is 4. I'll just move down here. Plus 1/2 for this third one, radical 14, radical 18, and 4. 1/2, radical 18, and 4. And this is approximately 58.661. And you will see why in a moment, but maybe you could already see why. This is a slight, I'll say relatively, a relatively slight under approximation. And the reason being is because the way that the concavity, let me use vocabulary, the concavity of this graph is concave down. The concavity of this graph makes it so that these, these tops here, or they're actually sides, makes it so that this side of the trapezoids is like slightly under the graph itself. Okay, now, sorry this is so long. All right, so now let's think about like when to say whether a type of Riemann sum or trapezoidal sum gives us an over or under approximation. We're going to have a criteria. So here I have left endpoint rectangles, right endpoint rectangles, trapezoids, and we're just going to draw one. And so in this column, I've got a section of a graph that is increasing concave up, increasing concave down, decreasing concave up, decreasing concave down. This might be a good section to fast forward as soon as you like get the point of what I'm doing. But make sure you pause at the end or slow down at the end for the punchline. So I'm going to go like this. All right, I meant to do this before I started. All right, so I'm just drawing a little x-axis everywhere. Yeah, this part for sure, guys, you could skip over something. All right, and then I'll be like, all right, so I'm drawing subinterval, a subinterval. I'm just doing this so I can go fast later. Okay, here we go. Left endpoint rectangle. All right, so I'm going to do for all of this whole top row, I'll do a left endpoint rectangle. Okay, so this is the base, left endpoint up to the graph, complete the rectangle. All right, base, left endpoint up to the graph, complete. Base, left to the graph, complete. Base, left, up to the graph, complete. Okay, so here the rectangles would give us an under approximation. It's under the graph. Here again, another under approximation. Here we would have an over approximation. Here we would have an over approximation. So you're trying to look for some criteria. Like when would a left Riemann sum give you an under approximation? When would it give you an over approximation? Now let's do right endpoint. Base, right, graph. Oops. Base, right, graph. Okay, and then this time over, so the opposite, right? The opposite of the left Riemann sum. Over, over, under, under. Okay, now trapezoid. So for a trapezoid, I use both of these endpoints to go up to the graph, and that gives you the bases. All right, so trapezoid. So up to the graph, connect. There's the height. Up to the graph, connect. Height, up to the graph, height, graph. Okay. And now, all right, here, over, under, over, under. Okay, now we've got to make some observations. All right, so now in each of these, so give me a moment just to write this down. So if, I'll say if F, Okay, so just simply knowing some characteristics of the function itself can allow us to say whether a left Riemann sum, right Riemann sum, or trapezoidal sum will give us an over or under approximation of the integral. So left Riemann sum would give us an over approximation if what? Guys, look at the left Riemann sum. Under, over, over. So what do these two over situations have in common? This one is decreasing concave up. This one's decreasing concave down. And then with the increasing ones, we have an under situation. So it's that, so we're going to have an over approximation if F is decreasing for a left Riemann sum. We'll have an under approximation if F is increasing. Okay, now the right Riemann sum is just, it's the opposite. Here we have our over approximations because, yeah, when the function is increasing. Here we have under approximations when the function is decreasing. Concavity doesn't matter for a right or left Riemann sum, whether you have an over or under approximation. The concavity doesn't matter. What matters is whether the function's increasing or decreasing. Now the trapezoidal sum, over approximation. Guys, here is where we have our over approximations for the trapezoidal sum. Now let's go up to the top, yeah. So here's our over approximations. Here we have increasing concave up. Here we have decreasing concave up. So really, for the trapezoidal sum, if we have an over approximation, it's not increasing or decreasing that matters. Okay, because here's an increasing case, here's a decreasing case, and they're both over approximations. So it's not increasing or decreasing that's going to determine if a trapezoid gives us an over approximation. It's the concavity. What these have in common is that they're both concave up. So if F is concave up, the trapezoidal sum will be an over approximation. And then down here we have the concave down ones. This one's increasing, this one's decreasing. That doesn't matter. It's the concavity. It's the concave down that means that the trapezoid will give you an under approximation. Okay, guys, we are almost done. All right, I'm just putting concepts together that are going to help you with the delta math. But the delta math is so easy once you get there, you'll see. Okay, so if the interval indicated by the integral is divided into the given number of subintervals of equal length, the equal length is important, what is the length of each subinterval? So here's how it goes, guys. Here's the length of our subinterval from 0 to, okay, so 0 to 15. 0, 15. All right. We want 5 subintervals of equal length. So, I don't know, 1, 2. That looks good, I guess. All right. 1, 2, 3, 4, 5. So if this whole thing is 15, it's split into 5 equal parts. What's the length of each subinterval? It would just be 15 divided by 5 equals 3. Okay, so that's the answer. What is the length of each subinterval? 3 units. Now there's another way of doing this, guys. Let me show you a faster way. So the way of doing it is this. Let me call this bottom endpoint A, the top endpoint is B, and then the number of subintervals is N. The formula for the length of a subinterval would be B minus A over N. This is the length of the interval, and then this is the number of subintervals. So B minus A over N. So here we would have 8 minus negative 8 over 8. This is 16 over 8. The answer there is 2. So these subintervals would be of length 2 if we had 8 of them. Let's do it again. So that's A, that's B, this is N. B minus A over N equals 20 minus negative 1 over 6. 21 over 6. All right. I mean, probably better just to leave it, but let me do it. I don't even need approximation because it's not irrational. So 3.5. Guys, I promise you, delta math is so super easy, okay? So do delta math. You'll see how easy it is. It'll take you two minutes. If you're confused at all about it, please text me and then I'll get you help right away. We could even do like a Zoom thing, and I'll show you how to do it. But there is delta math has videos that will show you, and it's super, super simple. All right, I'll talk to you later, guys. Bye-bye.